kind introduction. Yeah, as said, I want to present results of the DEEP and DPR projects. So two European projects we are coordinating at the Jülich Supercomputing Center. And it's about, well, as the title says, Taming, Heterogeneity in HPC. So this talk is about HPC, a quite narrow field. I will start with some motivation. So, yeah, not really why we are doing HPC, but what are the kinds of computers we are using in HPC. So I give a brief history of supercomputing architectures. And then we'll talk about why we are using heterogeneous systems today and why we have to do that also in the future. And then I present the key idea of how to organize heterogeneity, so how it's organized today and how we think it shall be organized in the future. And so this is the key motivation of these DEEP and DPR concepts, and I will present the DEEP concept, so the general concept, the hardware architecture that we are proposing and that we have implemented in this DEEP project, and then yeah, deriving out of that, so what does this mean for programming these type of systems, and so what changes in the way we have to program heterogeneous systems in HPC in the future. And then, well, I give a brief summary how we extended this DEEP concept within the context of the DPR project, and then give some very brief outlook into how we think this should further evolve in the future, going towards modular supercomputing, so that's how we call it. So to give a brief overview on the projects, so DEEP and DPR are two European projects, so projects funded by the European Commission. So in total, so we started with that about 5 years ago. So first with the DEEP project, so and both projects together, so we have 20 partners from all over Europe, as you can see on the map. So we received an EU funding of almost 50 million euros in order to do all this research. And so the DPR project is supposed to end in March 2017. So, but in order to motivate this type of research, let me just give you a brief overview on how the evolution of supercomputing was. So if you think about the first computers, so which popped up in the 40s and 50s of the last century, and if you look at today's definition of supercomputers, you would claim them as a kind of supercomputer. So that was specialized, very expensive, by the way, huge, so that they filled rooms, and so it made not really sense to differentiate between standard computers and supercomputers at that time. So the development of specialized supercomputers then started when computers became more general purpose, so in the 60s. So the focus of standard computers moved away from the scientific and engineering applications and moved more towards the enterprise applications. But of course, still the scientific and engineering applications played a major role. And so that was the point of time when, basically Seymour Cray started to say, well, so let's develop special computers for these type of applications. And this was when supercomputing and high-performance computing kind of started. So, and the focus of high-performance computing is still towards floating point operations, so basically linear algebra and, well, kinds of these operations. Well, in the first years, so really specialized technology was used. So they developed these vector processors. They used really expensive, high-speed electronics, so really different from the standard computers of that times. And well, so due to the fact that the number of systems was relatively low, so of course it was pretty hard to to refinance the development work that was necessary to develop these computers. So due to that, in the early 90s, it started that just standard processors were used in these supercomputers. So really the development moved away from these specialized vector processors towards just the standard microprocessor that were available, say, in workstations at that time. And then just many of these standard processors are glued together by a fast network. And so then this is this MPP, so this massively parallel systems architecture. So while this started with proprietary networks and proprietary software setups, so then in the middle or late 90s, it started that people thought about, well, so maybe let's go for commodity in all the components. So also use commodity networks and plug the system together by yourself, and then use open source software in order to give this hardware a kind of cluster thinking. So first of all the nodes are pretty independent, but then you have to add a layer which creates the cluster consciousness or the supercomputer consciousness into the system. So and then the newest trend is to go away from these homogeneous nodes glued together to a supercomputer to heterogeneous cluster systems. So and this will be the part I want to concentrate on. But first of all, to give a brief look on what are supercomputer architectures today and were in former days. So for this, it makes sense to look at the top 500 architecture of the top 500 list and the distribution of architectures. So the top 500 list is just the list of the 500 most powerful computers or supercomputers in the world. And as you can see here, so while there were what was a pretty interesting field of architectures when it started in the early 90s. So today, the list is basically dominated by so-called cluster computers. And these are computers which glue together the commodity processors with some commodity networks. And then there are about 20% of the system which are so-called MPPs, which also use these standard processors, but use proprietary networks and proprietary software stacks in order to put that together. So basically, these are these IBM Blue Gene systems that you might be aware of, and the highly scalable systems delivered by Cray. So this is the status today. And if you look at the evolution of supercomputing, what you will find out is that, and this plot just gives you a number of supercomputers which appeared during the last decades. And what you find out is that you have about a factor of 1,000 in compute power increase by decade, okay? And you might wonder where this factor of 1,000 comes from if you know that, and also this line, it shows just standard processors. If you know that by Moore's law, you would expect just a factor of 100 per decade. Basically the fact is that in HPC, systems became bigger and bigger. So more and more of the standard processors were glued together. So it's, has to be expected that this comes to an end. What's most crucial in this slide is the fact that if you look at the performance development of standard processors, you see that, well, during the last years, we get to kind of end of Moore's law. So this factor of 100 per decade, it actually stops. And so what we have seen during the last years is that you just get a factor of 10 per decade. So the question is, how can we evolve the performance of supercomputers in the same way as we did before? And the answer to that is that we have to go to some kind of many-core processors. Is it actually many-core processors as proposed by Intel in the the Knight's Corner and Knight's Landing architecture, so what's commercialized as Intel Xeon Phi, made it to use GPU-like systems. So as I already mentioned, this trend is due to the fact that Moore's law seems to come to an end. So even though the number of transistors still increases, so the single thread performance gets to an end. So frequency is not increasing anymore since about 15 years. And the reason for that is that the power consumption of the system is limited. And so you cannot really honestly go to beyond, say, 130, 150 watt per chip because you run into massive cooling problems. Which means that the idea to just glue together a general purpose processor will not work anymore in the future, right? So general purpose processors have some nice features, so that they have a really high single thread performance. Nevertheless, so still today, you have to use more than one core of them in order to put the performance into a single sockets. So nevertheless, they have some shortcomings. So the energy efficiency is quite limited, and they are quite expensive. So the idea is to use accelerators. And well, today there are basically two types of accelerators. There are the so-called many-core processors, so the Intel Xeon Phi processors, which had in the first generation about 60 cores, and now the second generation that was just presented during the International Supercomputing Conference last month in Frankfurt will have up to 72 cores. The other type of many-core processors around are these graphics cards-like processors, so the so-called GPGPUs, so general-purpose GPU processors, which basically come today from NVIDIA. And if you look into the top 500 list and the distribution of architectures, what you can find out is that already today, about 20% of the 500 systems employ accelerators in some way. Okay, so now the question is, how are these accelerators integrated into the system? And if you look at heterogeneous clusters today, what you see is, well, that there are these cluster nodes, which are just standard Xeon processor, interconnected by some flexible fabric, typically InfiniBand, and then attached to each and every node, there is an accelerator, so in this case, a GPU. So there might be one GPU, there might be two GPUs per node. The problem with this approach is that really the assignment between CPUs and GPUs is quite static, right? And actually, you have to do the ratio between CPUs and GPUs at the time of procurement. And then you might run into the problem that there are applications which can make use of, say, 4 GPUs. So, and they just find 1 or 2 GPUs, which means they cannot really fully exploit their potential. On the other hand, there might be applications which cannot make use of any GPU, so which means there is a GPU which is not really, which cannot do anything. So it just sits there and eats money. So the question is, how can we overcome this type of architecture? And the idea that we had, and which was the motivating idea for the Deep project originally, is to find an alternative integration. And the alternative integration, first of all, is quite obvious. So just put the cluster nodes and the accelerator nodes in an equal way into the fabric that you have. Well, there are some technical obstacles in order to achieve this, actually. But if you have this type of architecture, you're way more flexible. So at the point of time when you're starting the application, you can define how many cluster nodes you want to have, how many accelerators you want to have, and just put them together in a virtual way, so having a physical network there which allows that. And then you can define any ratio between cluster nodes and accelerator nodes which you require for your application. So that was a basic idea. And well, we started to do an implementation of that idea. And as I mentioned, there are some technical obstacles. So for example, you require to have accelerators which really can act autonomously in a fabric, in a network. And well, GPGPUs today do not provide this feature. But as we found out, so the accelerators provided by Intel at that time, so the so-called MIC architecture, or the Xeon Phi architecture, provide these features, at least partly. So and this is the hardware architecture that we came up with. So you have a standard cluster of Intel Xeon nodes. So this is a standard cluster, as you might see in every supercomputing center. And on the other hand, there is an additional cluster of accelerators, which we call booster, just to give it a name. So, and this booster consists out of Intel Xeon Phi processors, and in our case, interconnected by a different fabric, which is the Xtol fabric. It's a development by University of Heidelberg. And then, of course, you have to have some kind of interface nodes, which basically bridge between the two fabrics, and which has some other tasks due to the fact that the first generation of the Intel Xeon Phi processor was not really able to act autonomously. So you had to do some tricks in order to boot them. So you need a host processor in order to boot them. But once they are booted, and then there is a Linux operating system running on these nodes, they really can act autonomously. So, and yeah, we used this basic sketch of an architecture in order to do an implementation of that. So first of all, we created a cluster. So this is just a standard cluster, as I mentioned, interconnected by InfiniBand, provided by one of the partners of the project, the Italian company Eurotech. And then we extended the system by a so-called booster. So as you can see here, we created a backplane, then plugged into the backplane. There are some cards which provide the actual fabric, so the Xtol network, and then plugged into this card, providing the Xtol network, two so-called two KNC cards. So which means that logically this piece of hardware is two nodes. And the accelerators are directly connected to some network interface card. This is really an autonomous node of our booster side of the system. So I mentioned the Xtol fabric, so some details on that. It's a quite special fabric. So the basic idea of this fabric is that you don't have a central switch, but that you distribute your switch. So you have the NIC, which has a host interface, and then you have an integrated switch, and you have basically 6 output ports, and you can build a 3D torus out of these network cards. So what is really a nice feature is this SMFU, so this so-called shared memory functional unit engine. So we kind of abuse this engine in order to make the KNCs remotely bootable, so to be able to run them without an actual host processor. Furthermore, of course, we had to develop this booster interface node, so this is how they look like in hardware, and then integrate everything together to a so-called, to what we call the booster. So what you can see here is the actual piece of hardware consisting out of 384 Xeon Phi processors, so 2 of them integrated onto one of the blades, and then 8 of the blades into one half chassis, so 2 half chassis, and then in total we have 12 of these chassis. So you just see the ones on the front side. There's the same amount on the back side, and this implements our booster. So everything is water-cooled, direct water-cooled, so which means that you even can gain some of the power efficiency due to the fact that you can use free cooling for this type of system. In addition to that, we also developed a second system, which we call the ASIC evaluator. So the background of that is that, that there are 2 types of Xtol implementation, and the one which is ASIC-based, so which provides more performance, came a little bit late, so we had to find a different implementation for that, which is called the Green Ice Booster. Well, so it really gets too far to get into details there. So now the question is, now we have the hardware, and the question is which use can we make out of the hardware? The idea behind Deep and DBR is that we have so-called guiding applications. So we have applications from different fields of HPC with partners in the project providing these applications, and these partners then started to port their application to this new hardware architecture. So this is just a list of the applications. So what does it actually mean? So I have taken this climate simulation as an example, which is provided by Cypress Institute. And so starting from this hardware architecture, the way to put this climate simulation on that is as follows. So this climate application does not just do the pure weather part of the climate simulation, but combines the weather simulation with atmospheric chemistry simulations. And after an analysis of the actual application, we found out that it makes sense to split this application in a way that the base model, so the weather model, runs on the cluster side, and the chemistry model runs on the booster side. So which means that both parts are kind of independent and can evolve on their own. But then from time to time, they have to synchronize, so they have to exchange some information, which is then done via these booster interface cards. And this type of analysis was done for all the applications which were on the slide before, and then implemented. So now the question is how to implement that. So for that, we develop a quite complex software architecture. What you have to know is that basically all the applications in HPC make use of this distributed memory that you have provided by the underlying hardware architectures. And the programming paradigm which is used is the MPI. So, and what you have in the end in this system is an MPI stack on a cluster side, an MPI stack on a booster side, and then you have to find some measure in order to connect both, right? So the question is, how can you start an application on this type of system? So the basic idea is that you have an application which is based on MPI, you identify some parts of the application which shall run on the booster side of the system, and well, you start with the main part of the application, say on the cluster side, and then what you want to do is to start a highly scalable code part which can make use of the accelerators on the booster side of the system. So you have to do some kind of call in order to start the second part, which is different in this offloading compared to the standard offloading that you have in the standard heterogeneous clusters today, is that this part which is started is parallel. So this is not just one process running on one accelerator, or just a bunch of processes running on one accelerator, but you employ multiple accelerators, and these accelerators are even capable to talk to each other, so that they can do direct communication amongst each other without really utilizing the host processor on the other side. So the question is, what is the software, the programming paradigm to implement that? In fact, MPI, so the standard library for high-performance computing, already provides all the semantics required for that. So there is this MPI com-spawn call, which allows a group of processors running on one part of the system to start yet another group of processes and to connect them in a way that they can exchange information. So the MPI implementation we used in the project also provides, which is the power station MPI, gives the flexibility to actually use the MPI com-spawn, and furthermore to really exchange data, so to bridge between the two fabrics. So in the end, what the user sees is there's an MPI on the cluster, an MPI on the booster, employing the local networking technologies. Then there's this MPI com spawn in order to start a second part of the application on the other side. And there's this cluster booster protocol, which allows both parts to talk to each other. But in the end, it's just a global MPI, so the user don't really have to learn too much in order to make use of the system. Still, what the user has to do, he has to identify which part shall run on the other side, and then has to include the corresponding MPI com spawn call and MPI communication calls into their code, which is still quite hard work. So we implemented yet another ease for the application developer, which we call the offload abstraction, which is based on OMS, which is a software developed by Barcelona Supercomputing Center, also partner in the project. And here the idea is that you just just put pragmas into your source code. So you just annotate your source code. And then there is it's the OMS source-to-source compiler, which then extracts the corresponding part which shall run on the cluster side and on the booster side. Then you use the native tool chains on both parts of the system, creating two executables. And then the runtime system ensures that everything works, so that everything runs on the right side. So to summarize the advantages of deep are that, you are way more flexible. So you have a dynamic ratio of processors and co-processors. You can run just on one side or on the other side. But still, there are some points which we have not yet achieved in the deep architecture. And that was the motivation to go for DPR. And this is, we have not really we have not really provided some kind of I/O system. So and that was developed in DPR. And furthermore, we wanted to try out some new networking and non-volatile memory technologies which popped up during the course of the deep project. So what DPR implements, as I said, is some scalable I/O, and we used different systems which are quite common in HPC in order to really evolve this with some new features which make I/O way more scalable. And a different aspect are so-called resiliency features. So one problem in HPC, obviously, is if you have bigger and bigger systems, you have more and more components. And the reliability of a single component cannot really be increased, at least not if you want a system which is still affordable. So in order to meet this requirement, and since the number of components increases, this means that the overall reliability of the system decreases, obviously. So you have a certain probability that a single component will fail. If you increase the number of components, the overall probability that some part of the system will fail increases. Okay, so we introduced some measures in order to help with this resiliency problem. I will skip that due to time available. But I want to give at least a brief outlook on how future systems might look like. So what we have started is a kind of modularization of this heterogeneity that we have in today's supercomputers. Of course, you can think that further. So we have now just used this highly scalable booster. But of course, you can think about different accelerators. So specialized accelerators, for example, in order to include some data analytics into the HPC application. Or more specific, so we and Jülich are part of the Human Brain Project. And if you want to do brain research, it might make sense to have specialized hardware in order to implement neural networks, so-called neuromorphic devices. And you can think about other devices. So key problem here is, of course, you have to kind of orchestrate all the modules. And Yeah, we will propose yet another project to the EU in order to implement this orchestration. So which means that in the future, a HPC system running in Jülich might look like, so that is still you have in the core the cluster, which is just a standard cluster, but then you might attach a booster like that. You might attach some neuromorphic devices, so some neuromorphic system to that. Well, to be a bit more ambitious, you might think about attaching quantum computing devices to that, or even more exotic devices. So yeah, to summarize, within Deep and DPR, we really want to explore new ways on how to use and manage heterogeneity in HPC. And well, if you have any further questions, just raise them now. Come to our booth next door, or go to the project websites, which try to explain this in more detail. Thank you.